Okay, this is the 7.4 notes for the online trig class, trigonometric functions of any angle. The definition says let theta be any angle in standard position, which remember means that it is the vertex of the angle is at the origin and its initial side is on the x-axis on the positive side. So what they mean by that is that, let me do it in a different color. Here's your angle. It has a vertex at the center. There's the initial side, and then it opens either clockwise or counterclockwise around that. So if AB is the coordinates of any point except the origin on the terminal side of theta, so let's say this was AB, then the radius of this segment, so let's turn this into a segment instead of a line. So the radius of this segment is the square root of a squared plus b squared. That comes from the fact that any time you have an angle, you can turn it into a right triangle by dropping a perpendicular down to the x-axis. And A and B are kind of like the links of how much horizontal and vertical change is occurring. So the trig functions would be defined if you have that situation as the following. Remember, sine is opposite over hypotenuse. So according to my diagram, make the ink pen a little bit thinner, sorry. So according to the diagram up here, opposite is B and radius is R, so B over R. Cosine would be adjacent over hypotenuse, so that's A over R. Tangent would be opposite over adjacent, so that's B over A. And remember, these are just the reciprocals, so R over B, R over A, and A over B. Provided that none of the denominators equals 0, if that ever happens, so if any of these denominators are 0, the numbers in the bottom, that means the trig function of that angle is not defined because we are not allowed to divide by 0. So find the exact values of the trig functions for any angle is our example, and we want to find the exact value of each of the 6 trig functions for a positive angle theta if 4, -3 is a point on its terminal side. So we need to locate the point 4, -3, which would be 4 for x, that's 4 to the right, and then down 3 for y. So there's my segment from the origin. Remember, there's the initial side of that angle. So we're kind of creating a triangle with this, where the sides of the triangle have to do with the point, essentially. This is a 4. This is a -3. The signs do matter because that helps us figure out what quadrant we're in. We're in quadrant 4 here. To figure out your side for R, you use Pythagorean theorem because remember this is a right triangle. So -3 squared plus 4 squared equals R squared. So this is 9 plus 16 equals R squared. That would be 25 equals R squared. And we take the square root, and we always use our radius as a positive value. The only negatives that are involved in these problems are either if your legs of your triangle are in a quadrant that has a negative ratio. So my R is 5. So now I make my trig ratios. So sine of theta, and remember theta is this reference angle. When you're in standard form, theta is always the measurement that we get when we are measuring up to the x-axis from our terminal side. So for us, our sine of theta would be -3 for opposite over hypotenuse, so -3 over 5. Cosine of theta would be adjacent over hypotenuse, so that would be 4 over 5. Tangent of theta would be opposite over adjacent, so opposite is -3, adjacent leg is 4, so -3/4. That does not look like a 3. And then remember the others are reciprocals. So cosecant is the reciprocal of this, so it would be -5/3. Secant is the reciprocal of cosine, so secant theta would be 5 over 4. And cotangent is the reciprocal of tangent, so it would be -4/3. Notice something we haven't talked about yet, but In this scenario, sine and tangent were both negative because they are in a quadrant that has an opposite measurement that is negative. Cosine ended up being positive because it only uses the adjacent and the hypotenuse. And in this quadrant, those are both positive values. So we'll have a little rule in a minute. If it's not in this section, it's in the very next one that tells us which trig functions have different signs based on what quadrant you're in. All right, so let's look at example 2. Find the exact value of each of the 6 trig functions of a positive angle if negative 3, 3 is a point on its terminal side. Okay, so negative 3 is left 3 and then up 3. Make a triangle out of that. These are the legs they have to do with the point. This is the hypotenuse. There's my right angle, and there is my theta. It's my reference angle. So for this one, we have to look at the point, which is negative 3, 3. Negative 3 relates to the x-axis, so this is negative 3, this is positive 3. To Pythagorean theorem again to find our radius. So that's 9 plus 9, which is 18. Square root of 18 can be broken down, and we should, anytime you have a radical, you should go in its smallest terms. So there's a perfect square that goes in 18. Square root of 9 times square root of 2 makes square root of 18. The reason we break it down like that is square root of 9 is 3. So this is a 3 on the square root of 2. So then we go through our relationships. Sine theta is opposite over hypotenuse, which is 3 over 3 square root of 2. There is a problem with this. First of all, you're not allowed to have a radical in a denominator, but you have a 3 that reduces out. So that's actually 1 over the square root of 2. To get rid of the radical in the bottom, you multiply by something that would create a perfect square, since this is a square root in the bottom. So that would be square root of 2 over square root of 4, which is 2. So 2 on the square root of 2 is the sine of theta. Cosine of theta is adjacent over hypotenuse, so that's negative 3 over 3 square root of 2. Notice that that's going to work out exactly the same, except it's going to have a negative sign. Tangent of theta is opposite over adjacent, so that would be 3 over negative 3 or negative 1. Cosecant, you flip sine, but I would flip it right here before you rationalize, because that makes you not have to rationalize again. So 1 over the square root of 2, if we flip it, would be square root of 2 over 1, so that's easy. Secant of theta is the reciprocal of cosine. So again, use it before you rationalize. So that would be negative square root of 2 if we flip that. And cotangent is the reciprocal of tangent, which is negative 1. If you flip negative 1, it's still going to be negative 1. So there are all of those. Okay, so we want to find the exact values of the trig functions for quadrantal angles. Complete the following chart. So we have 0 degrees, which is right here at the x-axis. We're going to be looking at pi over 2. So this is 0 radians, I should say, not degrees. This one is pi, and this is 3 pi over 2. Now, in this scenario, it really doesn't matter what you let the radius be, because none of these are going to form triangles individually, because you have to look at these at one at a time. If you're at 0 radians, you can go out as far as you want, and this is going to have the same relationship no matter what. So it's a number, comma, 0. It's an x-intercept. So for this first one, so I'm not going to do all of these on the same picture because that might get a little confusing. So I'll draw different pictures for each one. So we're going to focus on the 0 case right now. If your point is 1, 0, that means that your x or your a is, let's see if we labeled that correctly up here on our chart originally. Yeah, see how x is always a and y is always b, the way we draw our triangles. So this will be our a is positive 1, and our b would be 0. Your radius is also 1, because if you're a straight line, you don't actually have a triangle, but if your point ends at 1, you do have a radius of 1. So remember, our formula is that sine of theta is the opposite over the hypotenuse. So opposite in this case, because you have to think for a second, is the one that is the height here. So that would be 0 in this case, but for us that would be b over radius. Cosine of theta was a over the radius, and tangent of theta was opposite over adjacent, so that's b over a. If you know that much, that'll get you through all of these. So, and essentially I don't like using, to me, I don't like using a and b. I actually prefer to use x and y. I'm just trying to be consistent with your textbook, because to me, y over r, x over r, and y over x makes a lot more sense to me. So that's kind of how I refer to it. So y over r would be 0 over, oh, and degrees, if you're 0 radians, you're also 0 degrees. So for sine, 0 over 1 is just 0. For cosine, that would be x over r. So 1 over 1 is 1. Tangent is opposite over adjacent. So that's y over x. So that's 0 over 1 again, which is 0. The problem is when you go to flip these, this becomes a 0 on the bottom. So that would be undefined. Secant would still be 1 over 1, so that's still going to be 1, but cotangent again would be 1 over 0, which is undefined. Okay, so let's talk about pi over 2 for a second. Pi over 2, if you pick any point on, is pretty much on the y-axis going up. Any point here would be a 0 and then a number, so make it easy, make it 0, 1. By the way, this is 90 degrees. So sine of 90 degrees, or pi over 2, is, remember, y over r. This again still has a radius of 1 because that's the length from 0, 0 to this point. So for us, this is y over r. That's 1 over 1, so that's 1. The cosine would be the x over the radius, so that's 0 over 1, which is 0. And tangent is going to be the y over the x. So y over the x here is 1 over 0, which is undefined. And then we do our flipping. So 1 over 1 flipped would still be 1. 1 over 0 for secant is actually going to be undefined. And 0 over 1 would be the last guy because that's the flip of tangent, and that would just be 0. So essentially you're kind of seeing a pattern. If it shows up as 0 in one of the original 3 trig functions, its reciprocal will be undefined. Okay, and then we need to talk about pi. So pi is over here in, between quadrants 2 and 3. So this is pi. And that is always a negative x value and a positive, or a 0 for y value if you're on this side of the x-axis. Again, your radius is 1. So this is 180 degrees, and the first part is y over r, so that would be 0 over 1, which is 0. The cosine is x over r, so that's negative 1 over 1, so that's negative 1. Y over x would be 0 over negative 1, which would still be 0. Cosecant is going to be the flip of this one, so that would be 1 over 0, so that's undefined. Negative 1 over negative 1 flipped would still be negative 1, and negative 1 over 0 would be undefined. And then we get to 3 pi over 2, which is down in the between the third and the fourth quadrants, and that would be a y value that has a negative y-intercept, and the radius is still a distance of 1, because the radius is just the distance that this measures. So this is 270 degrees, and we would have y over r, so that's negative 1 over 1, so negative 1 is our sine. We would also have x over r, so that would be 0 over 1 for our cosine, which is 0. Sorry, it's hard to look over here and write at the same time. Y over x would be our, so y over x would be our tangent, so that is going to be undefined. And for the last ones, we just flip it, so this would still be negative 1 if you flip it. This would be 1 over 0, which is undefined. And this would be 0 over negative 1, which is 0. You should notice some similarities. The things that are on the x-axis are always undefined for cosecant and cotangent. The things that are located on the y-axis are always undefined for tangent and secant. So just kind of a little pattern there between those. Okay, use coterminal angles to find the exact value of a trig function. Two angles in standard position are said to be coterminal if they have the same initial and terminal sides. Okay, so they both start here on the x-axis. The difference is this is A, this is angle A. We're going counterclockwise, and B goes clockwise. They both start and end at the same sides, but they measure differently. If you go this way, you're going to be a positive angle. If you go this way, you're considered to be a negative angle. That's just how we distinguish which way it's rotating. But they both are coterminal because of the end starting at the same side and ending at the same side, no matter which direction they go. Another way to be coterminal could be you could be traveling the same direction, but you keep going around and around. So this measurement from A is just one, it's not even a full rotation of a circle, it's just going from this side to this side. Whereas B, let me do it in a different color, they've tracked it not just once around the circle, but then they go all the way back around until they hit the terminal side again. So notice this would measure more than 360 degrees, but it is coterminal with the original angle. The cool thing about coterminal angles is that the difference between these two is going to be a multiple of 360 degrees, or 2 pi if you're doing radians. So if we want to find the exact value of the following, the first step is to figure out what this would be if it was, so we're going to convert between either 0 to 360 in degrees or 0 to 2 pi if you're in radians. So this 390, the way I convert it is I say, okay, if I have 390 degrees, take away one full revolution by subtracting 360. So that means that this is a 30-degree angle. So sine of 30 degrees is really what I'm looking for. Now, if you remember, this was in a previous section. Sine of 30 degrees is right here, and it was our special triangle. We learned that if you have a 30-degree reference angle, that this is a 30, 60, 90 triangle. Across from 30 is 1. Across from the hypotenuse is always double that, so we'll call that 2, and across from 60 was the square root of 3. And we did ask you to memorize what the ratios were for these reference angles of 30, 60, and 45. So sine of 30 is opposite, remember, over hypotenuse, so you can always draw the triangle, but you should memorize them. So that's 1 over 2. So that means that sine of 390 degrees, since those are coterminal angles, that means they end at the same location, is also 1/2. Okay, cosine of 420. So first we need to convert that into what would it be in one revolution. So subtract the 360. I have to borrow. So that's 60 degrees. So I'm doing cosine of 60 degrees. Now, if you remember one of the properties we learned in one of the previous sections, we learned that sine and cosine, if your angles that are inside add up to 90 between the two, then the answer is going to be the same, but I want to show you that visually. So remember, 60 degrees is a little bit taller, and it is going to then have a 30-degree angle, because remember, this has to add up to 180. So here's the 1, 2 is across from the 90, and this is square root of 3. So when you do cosine, you do of this angle, you do adjacent over hypotenuse. So notice it also ends up being 1/2. So this means that if that is 1/2, so is cosine of 420 degrees. Okay, 9 pi over 4. We need to convert that into a revolution between 0 and 2 pi. So you subtract off 2 pi, and to do that you're going to have to get a common denominator. That's why radians are a little bit harder. So I need to multiply top and bottom of the second fraction by 4, and that ends up being pi over 4. Now pi over 4 is 45 degrees. It's in quadrant 1. So really this is 45, 45, 90. I always write it in degrees when I draw the triangle because that helps. And that means this is an isosceles triangle, and the side lengths are 1, 1, and then square root of 2. Remember, we had those from our previous section. So then tangent is opposite over hypotenuse, which is 1 over 1. So tangent of 9 pi over 4 is the same thing as tangent of pi over 4, which is 1. Okay, let's look at secant of negative 7 pi over 4. We need to convert this. Usually when it's negative, instead of subtracting 2 pi, I add 2 pi to turn it back into a positive angle. And you may have to add or subtract multiple times, so this is not an exact science. You just have to get it between either 0 to 360 or 0 to 2 pi. So again, I'm going to get this to be a common denominator by making that 8 over 4, and this would end up being pi over 4 as well. So I don't need to redraw my triangle, so I'm looking at secant of pi over 4. I just need to remember what secant is. Secant is the flip of cosine. So when I look down here to find cosine, cosine is adjacent over hypotenuse, which is 1 over square root of 2. If you see this, the way to get rid of this and fix it is to multiply top and bottom both by square root of 2. You're rationalizing. That will cancel out the radical in the bottom, and then you just get square root of 2. And then for this cosecant one, notice it's a negative, so I'm going to add 360 to it. And that is 90 degrees. And remember, cosecant is the reciprocal of sine. And remember, we just talked about sine of 90 degrees. That is up here at the top. And imagine this point being 1, 0, and my radius is 1. Sine, remember, is it's opposite over hypotenuse, so that's the y over the r. So this is going to cause trouble because this is 1 over 0 over 1. 0 divided by 1 is 0, so that's a 0 in the bottom. So this one's actually going to be undefined. Okay, so that is how you handle those with coterminal angles. Okay, so this is finally what I was talking about a minute ago. I knew it was coming up soon. Your four quadrants break down very simply into certain trig functions have certain sign behavior in each quadrant. So we know that in the four quadrants, everything in quadrant 1 is a positive, comma, a positive. It's positive x's and positive y's. Everything in quadrant 2 is a left version of x, so that's negative, and a still up version of y, so that's negative, and then positive. For quadrant 3, everything is negative. You're left and you're down. For quadrant 4, you go right for x, that's positive, but you go down for y, so positive, negative. Remember, the radius of every single trig ratio for us, the radius of our triangle has always been positive. So what we're really looking at is what gets affected by either x or y being positive or negative. So remember that sine of theta had to do with y divided by the radius. And if your radius is 1, essentially all that matters, or if your radius is any positive number, all that matters is the sine of y. So sine depends on y. Depends on the sine, S-I-G-N, of y. Cosine theta is x over r. So cosine theta, we need to know sine of x. Tangent is the one that behaves a little bit differently because it includes both of those. You need the sine of both to determine what tangent's going to be. So notice that because this is, so all I do is the way I learned this is that I figured out which quadrants things were positive in. So in quadrant 1, sine is going to be positive because y is positive, cosine is going to be positive because x is positive, and tangent is going to be positive because you have a positive over a positive. You make that ratio. So all of the trig ratios are going to be positive in this quadrant. And by ratios, we mean the fractions that you get when you set up these ratios. Quadrant 2, the y is positive, so we know that sine is positive. Okay. X is negative, so that's going to make that one turn out negative. Tangent has to depend on both signs, so a positive and a negative together make a negative. So in this quadrant, the sine family is positive. What I mean by that is sine also has a reciprocal, which is cosecant, so it is also positive over here. In quadrant 3, y is negative, so that messes up sine being positive. X is negative, which messes up cosine being positive, but tangent is a negative over a negative, which means that the tangent family is positive down here. That means cotangent would also be positive. And then in this last case, this is where sine is going to be negative because the y is negative. Cosine will be positive because the x is positive, and tangent again has opposite signs, so it's going to be negative. So this is where the cosine theta family is positive. So all trig ratios are positive in quadrant 1 if your angle falls within that quadrant. In quadrant 2, only things that are related to sine, so sine and cosecant. Tangent and cotangent are positive in quadrant 3, and cosine and secant are quadrant and positive 4. Or quadrant 4, not positive 4, sorry. So what I do to remember this is I come up with a saying, and my saying is all science teachers, and you have to kind of add a word in here, are crazy, because you'll remember that. So all trig ratios are fine. Sine family is fine. They're positive, so these are when they're positive. So these ratios are positive in these specific regions. So all of the ratios are positive. The sine family is positive. The tangent family is positive. And the cosine family is positive. That means all other trig ratios that I did not list in the individual quadrants. So like over here, tangent and cosine are both going to come out as negative ratios. So knowing the relationship between the ordered pairs and the trig functions as seen in the earlier sections, the following quadrants with the appropriate signs for each of the 6 trig functions can be found. So I've already done this for you, we worked through it. So sine is positive in quadrant 1 and 2 and negative in quadrant 3 and 4. Remember, so for cosine, all, because that would include cosine, science, so that's not cosine, teachers, not cosine, are crazy, so that would be positive. So cosine is positive in these 2 quadrants, 1 and 4. For tangent, always positive, because all the families are positive in quadrant 1. Science, so not tangent. Teachers is tangent, are crazy, not tangent. So tangent and cotangent are positive in quadrant 1 and 3. So sine is good in quadrant 1 and 2 if you're talking about your ratio being positive. Cosine, it's 1 and 4, and tangent is 1 and 3. Example 5 says determine the sine of the trig functions of an angle in the given quadrant. So we're just kind of looking at a description here. It says name the quadrant in which the angle lies if sine is bigger than 0 but cosine is less than 0. So let's go back up and look at our picture because we haven't had a lot of time to digress and understand what we're looking at yet. Oop, it won't let me go back up. There we go. So sine, we need somewhere where sine is positive. So sine needs to be positive, but cosine needs to be negative. So it can't be quadrant 1 because I always look at the cosine one sec for this because it's easier for me. It can't be quadrant 1 because this is where everything is positive. In quadrant, the only other place cosine is, or excuse me, I'm supposed to be looking at where cosine's negative. So the only other places that we have where cosine are negative is quadrant 2 and quadrant 3. Let me go up a little bit more. If you notice, quadrant 2 has a positive sign but a negative cosine. So that means that if we want a positive sign and a negative cosine, we need to be in quad 2. And if you don't remember, your quadrants are always named in counterclockwise from Roman numeral 1 to 4. Okay. The last piece, the last page for 7.4 is about reference angles. Let theta denote an angle that lies in a quadrant. The acute angle formed by the, sorry, let me get my ink back on. The acute angle that is formed by the reference, well, no, that's not exactly how they want to state this. Sometimes these definitions are a little bit tricky. I always, it's going to be from the terminal side, that's how they're going to state this, of theta and the x-axis. So what we mean by that is wherever your angle terminates, you try to find the closest distance to the x-axis. So notice if you're in quad 1, that would just be the actual angle. If you're in quad 2, it's going to be the distance between. So this is what we call the reference angle. It has a little r on it. If you're in quad 3, you have to go up to the actual x-axis. And in quad 4, it's the remaining piece here. Okay, so wherever your angle ends, it's always the shortest distance to the x-axis. That's how you get your reference angle. So use a reference angle to find the exact value of the trigonometric functions. So for this first one, we have sine of 150, so that's in quadrant 2, because remember, this is 180 degrees, and this is 90 degrees, so 150 falls somewhere in here. So let me draw my angle in a different color. So here's my initial side, because it's in standard position. Somewhere over here is 150. So how do I find out what this reference angle is? Well, you ask yourself, what's the closest distance to get to the x-axis? It would be right here. The difference between this point right here where this angle measures and the angle where we stopped is this reference angle. So from 150 to 180, you would do 180 minus 150 and you would get 30 degrees. That means that this is a 30-degree reference angle. So really what we're looking for is what is sine of 30 degrees in quad 2. Okay, so if you think about drawing a little triangle over here, I always do triangles because that helps me. So here's my little 30 degrees, this is my 90-degree angle, and this is 60. So remember, across from 30 is 1, across from 90 is 2, and across from 60 is square root of 3. The only problem is you are now in quad 2. In quad 2, your x is negative and your y is positive. So this is negative because this is the x-axis measurement, because I'm thinking of drawing in my triangle right here. And this is positive because my y-axis value is positive. Radius is always positive. So if we do sine of 150 degrees, we're talking about opposite over hypotenuse. So this would be, from the angle of 30 degrees, that would be 1 over 2. So it actually is 1/2. Sine of 510, I would recommend getting that into a coterminal measurement that you can understand. So if we subtract 360, that would be 150. And we've already done sine of 150 degrees. So this is actually the same because these are coterminal. So that would have be 1/2. So sometimes things look different, but once you start thinking about coterminal angles and reference angles, they actually end up having the same measures. All right, find the exact values of the trig functions of the angle given the information about the function. If cosine is negative, and your angle is between pi over 2 and pi. That's 90 degrees to 180. So that means you're in quadrant 2. Find the exact value of the remaining trig functions. So the way I like to do these is I like to draw a picture and draw the triangle in. So I have cosine of theta. And this may not be how they do it in the videos that are tied into my math lab, but this is how I do it. Remember this top value, I don't really worry about the negative yet because that depends on what quadrant I'm in, but the top value is the adjacent value to my triangle, and this is the hypotenuse. When you're dealing with reference angles, you're always coming out from the center here, and then we have to drop down and create a 90-degree angle with the x-axis. So this theta right here, it has 2 and 3 as its adjacent and its height. So adjacent to the angle is the leg that's closest to it, and hypotenuse is always across from 90. The negative obviously needs to go with the 2 because this is a negative x value, which makes sense in quad 2. We're going to be searching for this missing y value here so that we can complete the triangle. So this is a squared plus b squared equals c squared. So negative 2 squared plus y squared equals 3 squared. That's 4 plus y squared equals 9. Subtract the 4 over, and y is the square root of 5. And in this case, it is going to be positive instead of negative because y is positive in this quadrant. So once you have that, you can actually write all of your ratios pretty quickly now. So sine of theta is opposite over hypotenuse, so that would be square root of 5 over 3. Cosine we already knew, so negative 2/3. Tangent is opposite over adjacent, so that would be negative square root of 5 over 2. Cosecant is the flip of this, so that'd be 3 over the square root of 5, and we need to rationalize it. So that would be 3 square root of 5 over square root of 25, which is just 5. Secant theta would be the reciprocal of this, so that'd be negative 3 halves. And cotangent is theta is the reciprocal of tangent. So negative 2 over the square root of 5, and again, you have to multiply the square root of 5 by square root of 5 to rationalize that. And anytime you multiply a square root times itself, the answer is just the number inside. So there are my 6 trig ratios. And then the final example, similar example, we have that sine is negative 2/3, and we're in the 180 degree to 270 degrees, so we're in quadrant 3. And remember, if you don't remember what these are, pi is always easy because it's half of 2 pi. 2 pi is a whole circle. But remember, you can multiply by 180 over pi to convert this to degrees. So I'm in quadrant 3. So I'm going to draw my right triangle down here. And I know that sine of theta is negative 2/3. Remember, in sine, opposite and hype are included. So here's theta, because the reference angle is always the distance from the hypotenuse to the x-axis, essentially. So opposite would be 2, hypotenuse would be 3, and this time this is negative. And this is actually going to come out to the same piece here, because you're going to have 9 minus 4 again once you square everything. So this would be, so I did Pythagorean theorem again, but it's the same ratio. We have a side that's a 2 and a hypotenuse that's a 3. And in this case, though, this is also negative. You do need to be careful about that. Notice that this one was negative because of this formula. This is negative because this is the left side of the x-axis, so the signs are important. So sine of theta we already know. Cosine of theta is adjacent over hypotenuse, so negative square root of 5 over 3. Tangent of theta is opposite over adjacent, so that would be negative 2 over negative square root of 5. I'm going to have to rationalize that. So multiply by square root of 5 over square root of 5. The negatives also cancel out, so that's 2 square root of 5 over 5. For cosecant, we flip the first one. So cosecant of theta is negative 3 halves. Secant of theta is 3 over negative square root of 5. I need to rationalize that. So it's going to be negative 3 square root of 5 over 5. And cotangent, I would flip it right here and go ahead and realize that the negatives cancel. It's square root of 5 over 2. So that is all 6 of those trig ratios. So that is the end of section 7.4.